The paper we want to review in this video is called Coverage-centric Coreset Selection for High Pruning Rates by authors from University of Michigan, Ann Arbor. The main problem that they investigate is the problem of one-shot coreset selection, in which the idea is to take a subset of training data and, given a specific pruning rate, do that, and then train a model and achieve an accuracy which is still high even though the entire dataset that was initially available is not used. A major problem with the previous approaches was the problem of catastrophic accuracy drop, which meant that when the pruning rate was high, the accuracy and the performance, respectively, would drop significantly. This paper theoretically and empirically investigates this problem. Proposes a novel coverage-based metric, and hypothesized based on that metric is that the worst data coverage is actually the reason behind the catastrophic accuracy drop. Inspired by these results, they propose a new approach called Coverage-centric Coreset Selection, or CCS. And empirically validated and showed that it actually works better. Here we have the definition for the one-shot coreset selection. And again go over the catastrophic accuracy drop under high pruning rate as the main problem with the already published approaches in this domain that are trying to target the problem of one-shot coreset selection. They go and explore the reasons behind the concept of catastrophic accuracy drop and show that the concept of data coverage is very important when it comes to measuring the performance in the high pruning rates. They generalize what was known before about the R cover coreset and add the percentage cover to the results. They propose another metric based on the area under curve of the PR curve. Then they investigate the idea of using this coverage in order to prevent the problem of catastrophic accuracy drop at high pruning rates. They do this by performing stratified sampling based on these importance scores. And for their empirical results, they evaluate this new approach on 4 datasets: Cypher 1000 and SVHN and Cynic 10. And for comparison, they have random, they have entropy approach, they have forgetting, they have L-tune scores, and they have AUM, showing that the CCS achieves better accuracy when the pruning rate is high, and when the pruning rate is low, it is still comparable with the other approaches. Consider a classification dataset with n samples, each one of them drawn IID from a distribution P that describes this data. One-shot coreset selection can be summarized as this optimization problem for this dataset, with S prime being a subset of S, and given a specific fixed budget as a ratio of the original dataset that can be selected, the goal is to minimize this expected value. Where this is the hypothesis based on training on the subset of dataset S, which is S prime, or the prune dataset. The other methods that have been introduced in this domain usually have a importance score assigned to each one of the items and then sometimes call it a difficulty score. And then they sort the examples based on that and then do the pruning accordingly. For example, forgetting or L-tune scores. The area under classification margin, the L-tune score, were other examples of these types of difficulty scores. In another work called Beyond Neural Scaling Laws, what they did was that they performed a self-supervised training and then they clustered the representations and assigned the difficulty score based on the distance to the cluster center, with the number of clusters arbitrarily selected. Now here you can see the problem of catastrophic accuracy drop. As you can see, the data pruning rate is increasing on the x-axis. At the moment we reach this part, the performance exponentially or very rapidly drops. This paper is mainly about showing that based on these usual importance scores, the important data to be used for training under high pruning rate is not covered in the set. The reason for which they mentioned to be the biased pruning of importance-based methods. Now let's see what they did. First, they extend the classical geometric set cover to the density-based partial cover problem. They use that to define a novel metric to compare the data coverage of different core sets. Then they show that the biased pruning of easy data leads to poor data coverage of core sets with high pruning rates. And lastly, they design a novel coverage-centric Coreset Selection method. First, see what the definition of R cover is. We define S prime as being an R cover of another set S, where if you take all the elements in S prime and consider the R radius ball around them, the result of the union of all these spaces is going to cover the entire S. In that case, S prime is an R cover of S. And this R can be used as a metric to measure the coverage of S prime on S. Now when it comes to set covering distribution, they extend it towards density-based partial cover. Here is a definition of the P partial R cover. Consider a metric space with X and distance D, and a set S from this space. And if you consider the measure mu such that d mu x by dx be p mu, and if you consider this, meaning that you take this probability multiplied by this indicator function, which this value is 1 over all of the points which fall into at least one ball of distance r with respect to distance d from point x, which x was a member of this S set. And now if you integrate this over the space of x, remembering that this was d mu of x, the result of this would give a percentage which determines the coverage of this set. And it is referred to as percentage coverage. So again, one component of this term was this indicator function, which is 1 over all of the spaces, which is 1 if for x falls into at least one ball of one of the elements of S with a radius of r, and then multiplying that by d mu x, where mu was the probability measure. For the R cover core set, one of the earlier works, mainly this work in 2017, for the risk over the entire training dataset. Now they want to extend that result to the P partial R cover, and the result is theorem 1. The assumptions of theorem 1 are as follows. First, n IID samples drawn from this distribution, where in each one of them the yi is basically the class index. The core set S prime, which is a P partial R cover for P mu, on the input space X. A positive value epsilon, which is larger than the difference between 1 and a percentage coverage. Now, if you consider the loss function that takes an example, basically like this, so this is going to be a function of x, right? If one can say that this function is lambda L Lipschitz continuous for all values of y and w, and bounded by value L, also the regression function being Lipschitz, also assuming the zero loss over the items in the core set, once the training is done, then we can say that the probability of the following equation is at least 1 minus epsilon to be true. If you consider the model that is trained using this core set over the example of the original data set, the absolute value for this is going to be bounded by the following. The implication of these theorems are, first, once you have a model trained in this core set S prime, which is a P partial R cover, then the training risk is going to be bounded by radius r times something plus another term, which this other term goes to 0 once the number of training samples goes to infinity. The other implication is that we want a small epsilon, meaning a large percentage cover, and a small radius, which would lead to a high probability over this bound on the loss. We know that with a small p, this bound becomes useless, and also when you consider the p's to be 1, this is going to be the same result as this paper. Consider a set S and a distribution p mu. It is clear to see that the cover percentage increases with the increasing of cover radius. Now, if you also take a percentage p and a set S, it's also possible to compute a minimum cover radius r. And then a PR curve can be basically drawn. In practice, however, the p mu is not accessible, so when you have the cover percentage p and cover radius r, you compute that r by measuring the fraction of the dataset that is covered. And for these covers, they use the L2 distance between the representations based on the final convolutional layers of a model that is trained using the entire dataset as a distance metric. Now let's look at figure 2 here. The lower curves are better, and we can see the blue curve is actually lower, which is without pruning. An important point to observe here is this area. They consider these PR curves and hypothesize that the area under curve of this PR curve is a good metric to assess the quality of the selected core set. They propose that lower values of AUC of this PR curve is going to indicate a better coverage. Now here's the proposition 1. If you have a metric space X and D, a distribution P mu, a cover percentage P, and a set S, and if you also have this curve FRP, which gives the value of radius given P, resulting in a PR curve, and showing the mapping between P and R, if this FR is Riemann integrable, the AUC of this PR curve can be written as this, is going to be equal to this value, meaning that the expected value of the distance between X and the set S, X being sampled from the distribution P mu. And this DSX is basically the point to set distance defined as here, meaning that you find the element from S that is closest to X based on this distance D, and that distance is going to be the distance between X and S. So based on this, the AUC PRS is going to be equal to the average or the expected value of the D of S and X based on these. So AUC of PR based on this proposition can be estimated with the test set as this. So it's going to be by sampling X from D test as a proxy, you could see that AUC PR of S can be estimated. If you look at table 1 here, you have pruning rates and you have random forgetting AUM showing the AUCPR of these corresponding curves. This goes back to figures similar to figure 2. Now, what you can see here is that as you increase the pruning, let's say up to 90%, the area under classification margin of forgetting end up having AUC values of larger than random selection, which also is consistent with the fact that we know that they perform worse than random selection under high pruning rates. And this is the result of worse data coverage. If you look at accuracy as a performance metric and look at random AUM and forgetting, and the without pruning as a reference here, you can see that as this area under curve value increases, or in other words, as the coverage drops, we can see that the AUM and forgetting have this significant drop over here. Based on these observations, they propose the Coverage-centric Coreset Selection, which is the algorithm, which works based on existing importance scores such as L2 and AUM, forgetting, and entropy. However, they don't just simply pick the highest scored elements. Instead, they use the stratified sampling to make sure all basically distributions are fairly represented. They first divide the population into different exclusive strata, then they do random sampling based on a desired pruning rate. They divide all training data into k even strata, and this way, by doing this stratified sampling, they make sure that high density strata still gets some budget to guarantee a good data coverage. Here's a detail of how their algorithm works. So first, they consider a ratio beta of the data set. For example, if it's L2, the beta percentage of the highest elements, And they mentioned that usually, like, let's say misleading examples have the highest score, so they want to focus on the actual worthy examples. So first they remove a beta percentage out of this data, and then they work with S prime. S prime will be split into K strata as a second step. And based on basically a pruning rate alpha, you want to have M elements, and then you want to have this coreset SC. So in this loop, unless beta is an empty set, they evenly sample MB elements from it, add this to the coreset, remove that item from remove basically that stratum, and continue until we have M elements in the coreset SC, and then they return this SC. So basically it's just a stratified sampling based on an importance score. Here's also an interesting figure. So consider the area on the margin as one of the examples of these importance scores, something like L2. So if you consider the state-of-the-art methods that just pick like the highest scoring elements, they would select this ratio of the data distribution. So they're not going to have easy examples over here. And at the same time, they have the highest scoring elements, which could, for example, be noisy examples. Now, in the coverage-centering Coreset selection, the approach in this paper, they would select this ratio. So you have easy examples and you have hard ones, and you have like an evenly distributed stratified sample of the data points. Now, in the results in Cypher 10 dataset, they show that in the low pruning rates, the result is comparable, and the high pruning rates, the results are actually superior. In Cypher 100, we also have the similar score. They also performed an ablation study looking at the relationship between K and the accuracy, K being the number of strata, and I can show that it's not super sensitive to it. So the first conclusion is that this K is not a very sensitive hyperparameter. In analyzing beta, the cutoff rate, basically the percentage of the top scoring items to be removed before proceeding with the algorithm, they show that as the pruning ratio goes higher, let's say for example the 90%, you can see that the optimal hard cutoff rate actually increases. They hypothesized that this could help allocating more budget to high density strata, and therefore help the performance in this way. Lastly, they do an ablation study over the stratified only and prune hard only methods and compare it with their proposed CCS. For example, under the high pruning rates, they show that this is stratified only and the prune hard only both work better than, let's say, forgetting as an example of the state-of-the-art methods, but they still, roughly speaking, at least the stratified only works worse than the random. And only pruning the hard examples works fine in this case, but it still does not work as well as the CCS does. And this concludes the review of this paper, which tried to understand the catastrophic accuracy drop and the reasons behind it, extended the classical geometric set cover to density-based partial cover, proposed a data coverage metric, and provided a reason why these state-of-the-art approaches could lead to poor data coverage, and designed a novel algorithm called CCS.